Welcome to Chapter 5, the final chapter of our supercritical fluid technology series. Here we explore the cutting edge of SCF technology, how it's tackling the PFAS forever chemicals crisis, revolutionizing pharmaceutical manufacturing through particle engineering, and enabling emerging applications from 3D printing to energy storage. We'll conclude with a comprehensive market analysis and outlook for this rapidly growing field. This chapter connects all the fundamentals we've learned to the future of supercritical fluid technology. Per- and polyfluoroalkyl substances, or PFAS, represent one of the most challenging environmental problems of our time. The carbon-fluorine bond at 485 kilojoules per mole is among the strongest in organic chemistry. This extreme stability means PFAS don't break down naturally, persisting in the environment for decades to centuries. They bioaccumulate, concentrating up the food chain and in human tissues. PFAS have been detected in the blood of 97% of Americans. Health effects include links to cancer, thyroid disease, and immune system suppression. EPA health advisories continue to be lowered as research reveals greater toxicity at smaller concentrations. Supercritical water oxidation is one of the few technologies proven to completely destroy PFAS compounds. At 550 to 650 degrees Celsius and 25 to 30 megapascals, with residence times of 30 to 120 seconds, SCWO achieves greater than 99.99% destruction. The EPA verified this performance in 2023 and 2024. The process breaks the notoriously strong carbon-fluorine bonds through radical chain reactions. Products are carbon dioxide, water, and hydrogen fluoride, which is immediately neutralized to calcium fluoride, a stable naturally occurring mineral. Commercial facilities from 374 Water, Revive Environmental, and General Atomics are now operating. Pharmaceutical manufacturing has embraced supercritical fluid particle engineering for precise control over drug particle properties. 4 main methods are used. RESS, rapid expansion of supercritical solutions, dissolves the drug in supercritical Co2 and rapidly depressurizes to form particles of 0.1 to 10 micrometers. SAS, supercritical antisolvent, works for drugs that don't dissolve in Co2 by spraying organic solutions into supercritical Co2, producing particles as small as 20 nanometers. PGSS, particles from gas-saturated solutions, atomizes Co2 saturated melts for high-throughput production. SFE, supercritical fluid extraction of emulsions, produces nanoparticle suspensions directly in water for injectable formulations. Active pharmaceutical ingredients require exceptional purity, and supercritical Co2 extraction delivers. Compare conventional ethanol extraction to supercritical Co2 for a compound like nicotine. Conventional achieves 85% purity with residual solvent requiring removal, while supercritical Co2 achieves 99% or higher purity with absolutely zero residual solvent. For artemisinin, the Nobel Prize-winning antimalarial compound, supercritical extraction achieves 92% yield versus 70 to 80% conventionally, greater than 98% purity, 40% faster processing time, and zero solvent residue. The inherent compliance with ICH Q3C solvent residue guidelines is a significant regulatory advantage. The supercritical fluid technology market shows strong growth across all segments. The SFE chemicals market is valued at $2.9 billion in 2024, projected to reach $7.9 billion by 2034, representing a 10.9% compound annual growth rate. The SFC instruments market is growing more modestly from $1.7 billion to $2.25 billion. By application, pharmaceuticals lead with nearly 40% market share, followed by food and beverage at 28%. Regionally, North America holds 38% of the market, but Asia Pacific is growing fastest at 13.5% annually, driven by expanding pharmaceutical manufacturing in China and India. Supercritical fluid technology is expanding into new application areas. In 3D printing, supercritical Co-2 creates microcellular polymer foams for lightweight filaments, produces fine spherical powders for selective laser sintering, and removes support materials from printed parts. For energy storage, compressed Co-2 energy storage systems store excess grid electricity by compressing Co-2 into underground reservoirs, achieving 60 to 70% round-trip efficiency at scales from 10 megawatts to gigawatts. Waterless textile dyeing using supercritical Co-2 eliminates water use entirely, reduces energy by 50%, and achieves better dye fixation, with major brands like Nike and Adidas already using the technology. It's important to acknowledge the challenges limiting broader SCF adoption. Capital costs are 3 to 10 times higher than atmospheric processing equipment due to high-pressure vessels and specialized materials. Scale-up is difficult because mass and heat transfer change with scale, and safety considerations increase. Pure supercritical Co-2 is limited to nonpolar compounds, and while co-solvents extend the range, they reduce green chemistry benefits. Supercritical water systems face severe corrosion, with equipment lifetimes measured in months rather than years. Compression energy is significant, requiring good heat integration for economic operation. And specialized expertise in high-pressure systems is required but limited in availability. Despite these challenges, the future outlook is positive. Integration with renewable energy is advancing, with solar-powered supercritical extraction already demonstrated. Supercritical Co-2 power cycles are ideal for concentrated solar power plants. Artificial intelligence and machine learning are accelerating process development through property prediction, process optimization, and scale-up modeling. New reactor designs, including microreactors for enhanced safety and transpiring wall reactors to eliminate corrosion, are emerging. Regulatory drivers continue to strengthen. EPA PFAS regulations are tightening, the EU Green Deal favors green solvents, and the FDA is encouraging continuous manufacturing, where SCF technology excels. Let's conclude our 5-chapter journey through supercritical fluid technology. Chapter 1, establish the fundamentals, critical point, phase behavior, and unique properties. Chapter 2 explored supercritical Co-2 as the accessible, green workhorse solvent. Chapter 3 revealed supercritical water's extreme capabilities for waste destruction. Chapter 4 showcased industrial applications from coffee to power generation. And Chapter 5 examined advanced topics and the growing market. Key megatrends drive this technology: sustainability demands, tightening regulations, quality requirements, efficiency pressures, and remediation needs. The market is projected to grow from $2.9 billion to $7.9 billion by 2034. Thank you for joining the Supercritical Fluid Technology series. The future truly is supercritical.